Have you used the product rule many times in calculus and now want to rigorously and intuitively understand why it's true? This video is for you. Here we have the product rule, which states that if f and g are differentiable functions at x equals to a, then fg, the product of f and g, is differentiable at x equals a, and a formula for the derivative of fg, which is fg prime of a, the derivative at a is f prime of a times g of a plus f of a times g prime of a. We're going to rigorously prove this using the limit definition of the derivative and also intuitively understand why this is true, all in 10 minutes. So let's just dive right into it. So what we're going to do is we're going to take off the original definition of the derivative and understand where the terms in the product rule come from, which can seem mysterious, and also understand very rigorously how to justify it as a mathematician would. And then once you've justified it, the cool thing is you can freely use it whenever you like. And it's such a powerful rule, as you know, if you've used it in calculus. So here what we want to do is we want to look at the derivative of the product at a, and by the limit definition of the derivative, that is the limit as h goes to 0, so I'm going to write it here, limit as h goes to 0 of f of x plus h, or f of a plus h, times g of a plus h. So this is the product fg evaluated at a plus h. By definition of the product of two functions, you just multiply the values at the point, and then you take f of a times g of a. So here I'm going to write f of a times g of a. That's going to be the numerator, and we're all going to divide by h. Okay, so this is the rate of change of f of x times g of x at x equals to a. And now that we've got this, we want to understand how to manipulate this limit. Okay, so how do we use the fact that f and g are differentiable to find this limit? So I'm going to show you a bit of intuition. Okay, before we dive into it, I'm going to show you a bit of intuition of how this works. So here's a really cool way of looking at it that I really love. That is, you have a rectangle in the plane. Okay, so I'm going to use a red marker here. We're going to have a rectangle. We're going to have the value f of a plus h. So this is a schematic. Okay, so f of a plus h need not be greater than f of a, but the intuition is going to be here. And once we've got the intuition in math, we can justify it rigorously. Okay, you can strip away the picture and justify it. But first, we're not computers. So first we think about the intuition. So here you're going to have two rectangles, this rectangle and this rectangle. Okay? And what we're trying to figure out in the numerator here is the area of the big rectangle, which has base f of a plus h and height g of a plus h, minus the area of the small rectangle, which has base f of a and height g of a. Okay, we want to subtract the two. And here's the cool thing we can do. We can subtract the areas of the two rectangles by as follows. We're trying to find the area of the region in between the two rectangles, right? And that region can be split up in the following sense. You can split it up as the following. You can split it up like this. Okay, so here you have this shaded area, which I'm shading in black, and you can also have a shaded area in green, for example. So here I'm shading this area in green, and we can add up the two. So what is the black area going to be? Okay, the black area is going to be g of a plus h times f of a plus h minus f of a. Right? It's a rectangle, and its base is going to be f of a plus h minus f of a. Its height is going to be g of a plus h. So we get that. And then the green area, we can add up, we can find out that too by the base times height formula. That's going to equal to, the base is going to be f of a, and the height is g of a plus h minus g of a. Okay, so we're going to get f of a times g of a plus h minus g of a. And this schematic suggests to us that actually this numerator here is equal to that. Okay, now this is why I'm saying this is intuition, because many proofs they will just dive into that, and it's kind of see, how do you do that? How do you split it up in this way? And the cool way about splitting up in this way is immediately see we can exploit what we know about the derivatives of f and g, right? That's what we want to do, because the information we're given is f and g are differentiable. So here you have f of a plus h minus f of a. Okay, that's going to be related to the derivative of f, and the g of a plus h minus g of a, that's going to be related to the derivative of g. So here we can write this out in the same way as I did there, but using the following trick, which is to add and subtract something from the numerator. So I'm going to write down limit h goes to 0 of f of a plus h times g of a plus h minus, okay, minus f of a times g of a plus h. So I'm subtracting some new term, okay, f of a times g of a plus h, which is coming there as well if you like. But now I have to add it on. Because I've subtracted it, I have to add it on so that it cancels off. So you get f of a times g of a plus h minus f of a times g of a. And the whole thing is going to be divided by h. Now what we've done here is basically we have just written this out. G of a plus h can be factored from the first difference times f of a plus h minus f of a, as you see in that picture, and then f of a can be factored here times g of a plus h minus g of a. So you can factor them out like you do in that way, and now what you can do is you can get two different limits you can find using the derivatives of f and g. Okay, so I'm going to take this, I'm going to erase this, and I'm just going to now factor this as I've done there. Okay, so it's exactly that factorization there. So we're going to erase the top, so I'm going to erase this out here, and just write it in factored form. Okay, and in fact I'm going to erase this here to create some board space as well. So we've now reduced that the limit is going to be the limit as h approaches 0 of g of a plus h times f of a plus h minus f of a plus f of a times g of a plus h minus g of a. Okay, times g of a plus h minus g of a, the whole thing divided by h, and that's now going to be, you can split up the limit, so you can write this as limit h goes to 0 of g of a plus h. So when you split up a limit as of a sum as a sum of limits, you have to make sure both limits exist. Okay, you can't freely do this in limits. When you split it up, you have to know both limits exist, but we have a pretty good sense that f of a plus h minus f of a by h does exist. It's a derivative of f at a, and similarly for g. So we can say this is limit h goes to 0 of g of a plus h times f of a plus h minus f of a divided by h. And then we're going to get plus limit h goes to 0 of the other term, which is limit h goes to 0 of f of a times g of a plus h minus g of a divided by h. Okay, so we get g of a plus h minus g of a divided by h. And now we've got these two limits, we can now evaluate them separately. Okay, so now we're almost there. Okay, we're almost there, and this kind of gives the intuition for where the product rule comes from, where the two terms come from. This is going to be a well-defined limit. It's going to approach the derivative of f at a. This is also going to be a well-defined limit. It's going to approach the derivative of g at a. The f of a here is a constant, right? H goes to 0, f of a doesn't change. But what about the g of a plus h? What happens there? Okay, so this is where we're going to have to use another fact that I won't prove in this video, but will be there in another video on my channel. So check out my channel. I've got comprehensive videos on all levels of math, from basic to advanced. I'm building a library of math at all levels, and I'm going to have a video explaining why differentiable functions are continuous. Okay, so the intuition is basically that, the very quick intuition, I'll tell you very quickly, is g of a plus h minus g of a by h. If that limit exists, that's to say g is differentiable at a, then the top better approach 0. Because if the top doesn't approach 0, the bottom is approaching 0, it's going to be something non-zero over 0, which is not going to exist. So if the top approaches 0, that says g is continuous. That value is close to a, the value at g at those values is close to g of a. And so here we've got g of a plus h is going to approach g of a. Okay, so now that we know that, we can actually write this out. I'm going to just erase this here, this schematic, this nice little figure here. And you know, this figure is a pretty cool figure for algebraic manipulations in general. So now what we're going to do is we're going to write this out. This is going to be limit h goes to 0 of g of a plus h. Okay, so we're going to use, maybe I won't write it all out, we're going to use the product rule basically, right? So because these two limits both exist, we know that the product of the limits is the limit of the product. So you can always split assuming you know both exist. Okay, you have to know both exist. Then you can say that this is just going to equal to that limit which I've just erased, which we know is g of a, as we just explained. So it's g of a times f prime of a, using the fact that differentiable functions are continuous, plus f of a times g prime of a, plus f of a times g prime of a. And that's going to be the product rule. Okay, so we've basically shown that the derivative of the product exists. It is just the limit definition of the derivative. It's going to be that formula there. So thank you so much for watching. Hope you enjoyed the video, which gives an intuition for why this is true. And I have videos on proving other facts about derivatives too. So I'm trying to do math. You know, if you're just trying to pass exams in your calculus course, I'm here for you. If you want to deeply understand why things are true and go into proof-based math, I'm also here for you. I'm trying to support as many people as possible. No matter what your goals are, if it has anything to do with math, I'm here to support you. I'm building a project of infinite free accessible math education worldwide, And I want to support as many people as possible, even people who don't have access to internet. Right now I'm doing this through YouTube, which is a restriction I have, but once I get big and I get more resources, I want to support as many people as possible to make free accessible math education worldwide at all levels. I've received a university faculty-wide teaching award at Princeton. I have a lot of experience teaching advanced math. I spend my time thinking about math. I'm a research mathematician, and I'm giving you a unique angle on math as a journey rather than as a bunch of concepts. So if that all sounds appealing to you and you want to support my vision, and I've supported you in this video, if I've supported you on this video and you want to support my vision, please don't forget to like, subscribe, and share with friends and family who could also benefit, students, classmates, to spread the word about this channel so that I can help as many people as possible and support as many people as possible, as well as supporting you. So please don't forget to do that. Drop a comment down below. I'd love to hear from you. I really love engaging with viewers, so don't be shy to drop a comment down below. And I'm super excited to see you in the next video.